Hello, my name is Carter-Schwendler, and I'm with the CommPlus Performance team, and I'm going to be talking about component load balancing with CommPlus. First, I'll go over the agenda. First, I would like to talk about some of the reasons for load balancing, why you'd like to do it, why it's a good thing, why it helps you. Then I'll go into a general overview of load balancing, some of the issues, some of the definitions, things that don't relate specifically to component load balancing with CommPlus, but are general issues that you have to concern yourself when you talk about load balancing architectures. Then I'll go into the specific architecture of CommPlus load balancing, component load balancing. I'll go into the algorithm, and I'll go into some detail of how the algorithm actually works. Then I'll move on into actual performance numbers, things that we measured in our lab that demonstrate the scalability of CommPlus component load balancing. I'll finish up with a few comments on those numbers, and then we'll have questions. Here's a definition of load balancing. Basically, load balancing means that the work is divided among a number of resources somehow. The architecture really defines what the unit of work really is, and for the purposes of this talk, I'll describe the unit of work as the balanced unit of work, the balanced unit. And that unit of work can be very fine-grained or it can be coarse-grained. That is, you can have very large chunks of work that you delegate among the resources, or you can have very small chunks of work. Now, the basic benefits of load balancing are first, scalability. This is the first one that most people think about. If you happen to need more throughput, even if perhaps your current hardware supports all your current needs, it's very reassuring to know that as your needs grow, all you have to do is add another machine and you're able to satisfy these new needs. Availability, that's also naturally very important. A node can be taken offline, it can fail, anything can happen to it, and the availability of the application itself is not affected. The clients still see the application without any break. Flexibility is also an important aspect of component load balancing, or load balancing in general. If you need to add hardware or remove hardware, it just makes things easier to maintain because you can pull things in and out as you want. Now, parallelism in general can be very coarse-grained. That is, the balanced units are very large, or it can be fine-grained. That is, the balanced units are fairly small. Generally, a coarse-grained load balancing algorithm can lead to unequal utilization of resources. If you have very large chunks of work, that work can it's harder to evenly distribute large chunks of work among many resources. But at the same time, fine-grained parallelism, it's easier to distribute over multiple resources, but at the same time, you may have significant overhead with it. Coarse-grained parallelism tends to perform very well if you are able to evenly distribute the load. But again, the overhead of fine-grained parallelism, depending on the architecture, may be worth the price of some unequal resource utilization, depending on the specifics of the application. Component load balancing in particular, the way it works is that component activations are the balanced unit of work. That is, the act of a client calling co-create instance against a load balancing server is what gets load balanced. Specifically, a client will call co-create instance to create an object against a load balancing server. Then the load balancing server selects the appropriate cluster machine. Now, what I mean by appropriate, I'll describe in more detail when I talk about the actual algorithm. The load balancing server then delegates this request to the target machine, and the target machine returns an object reference to the client, and then directly to the client, so the load balancing server, or the router, is no longer involved. Now, the programming model for this is that, again, activations are load balanced, And the implication of that is that when a client holds on to an object reference between method calls, then that client is bound to the server that the load balancing server initially allocated for it. And it will be forever stuck to that server as long as it holds on to the reference. But it also means that existing MTS applications will balance without modification. All you have to do is bring your existing MTS application into COM+, make it load balanced, and it will work. But one thing that I really need to emphasize is that simply because activations and co-create instances are the balanced unit of work doesn't mean that the programming model should be changed. It is still better for the clients to hold on to references between method calls. You end up with a coarser grain of parallelism, but that isn't necessarily bad. Now, the actual load balancing algorithm is a hybrid of response time and round robin. Now, response time, as I define it here, is where the load balancing server polls the other machines and checks the response time for that particular object and all the other machines. It then chooses the fastest machine and sends all requests to that machine until the next polling interval has expired. Round robin is where you have a list of all the machines and you simply go through that list one after another. Now, the actual algorithm as COM+ implements it is a hybrid between these. Instead of just doing response time or round robin, the load balancing server polls the cluster machines and then makes an ordered list of the machines in order of response time. So the fastest machine is on top of the list and the slowest machine is on the bottom. Then the load balancing server delegates incoming requests to this list of machines in order. And it does a round robin algorithm through this list of machines. So for a very short polling interval, the algorithm is basically response time. The round robin doesn't really have a chance to kick in. The polling interval is very short, and probably the load balancer will only get to the first one or two entries in this list, and you basically have a pure response time algorithm as I defined it. On the other hand, for a very long polling interval, you basically have round robin. You can think of an extreme example where you set the polling interval to be a week, for example, in which case for that entire week you're just cycling through the list of machines one after another. And then really the fact that the list was ordered based on the response time at some time in the past doesn't really make any difference. And the load balancing server can be included or excluded from the list of machines available for execution. So for example, the load balancing server can be a dedicated router that only delegates requests to other machines, or you can set it to activate requests locally. And I'll get into that a bit later. Now again, with the coarse and fine-grained parallelism that I was talking about before, that really ties into the activation ratio. And the activation ratio really indicates how coarse or how fine-grained your parallelism will be when you use component load balancing with COM+. As you may or may not know, MTS and COM+ support just-in-time activation. That is, if you have a component that calls set abort or set complete and the component goes away, the client can still hold on a reference to that object, and when the client makes the next method call, the object will be created. Now this is very much faster than if the client releases the object in between and has to call co-create instance for every method call. So it's very much an optimization. However, even if you say you're using JIT, you are using just-in-time activation and holding on to references between method calls, objects still must be created at some point. So I introduced the concept of activation ratio, which is, as I define it, the percentage of calls that don't require an object creation. Now, in real life, this depends a lot on the actual scenario you're using. It depends on the application, of course, on whether or not the client holds on to a reference between method calls, but it also depends on the usage patterns of that application. If a user is likely to open and close the application many times throughout the day and only do 1 or 2 transactions while that application is open, you're very likely to have a very low activation ratio, even though you're using JIT. However, if you have an application where everybody opens it up in the morning and keeps it active all day long, then you're likely to have a very high activation ratio. And the way I define it, 100% activation ratio is 100% JIT, where the components were created at some arbitrary time in the past, and now all that's happening is method calls, while a 0% activation ratio is a no JIT scenario where every method call is accompanied by a co-create instance. Now, I'll be talking about performance numbers first, but before I get into that, I'd like to talk about the setup that I used for running these performance tests. First of all, I used the Windows DNA Performance Kit, and I'll give you a point from where you can download that later on. The component was written in ATL, and it uses ODBC to do a single debit-credit transaction, and it uses a single stored procedure on SQL Server. Now, and every method call in this test was accompanied by an object creation. Now, this won't give you the fastest performance, but it is the most difficult case for the load balancing server to scale. It puts the most stress on the load balancing server, so I wanted to show that load balancing works in the worst case scenario. And here are the results. As you can see, the dark line indicates the transactions per second where the router is not included as an application server. The lighter colored line indicates where the router is included as an application server. On the y-axis, you have the transactions per second. That is the number of debit-credit transactions that occurred in 1 second. On the x-axis, you have the number of machines. Now, the way I define the number of machines is it includes all of the machines in the test, regardless of whether or not the load balancing server is an application server or if it's a dedicated router. So, for example, where you have 3 machines, for the dark line where the router is not included, that means that you have 2 application servers and 1 dedicated router. On the other hand, for the lighter colored line where the router is included as an application server, that means you have 3 application servers. And as you can see, where the router is not included, the performance scales quite linearly as you add machines. And it also scales well where the router is included. However, at some point, the activation and the servicing of requests begins to interfere with the routing and the delegation of requests, and the performance begins to taper off, and the router itself becomes a bottleneck. Now, here are some comments on the results. As you may have noticed from that slide, the maximum performance I was able to obtain with 8 machines was 800 transactions per second. Now, one way to put this in perspective is that with this test, you had very fine-grained parallelism, and the load was very evenly distributed. Now, you may think that it may be better to have a co-create instance with every method call and have this fine-grained, even load distribution, but that isn't necessarily the case, because with a 100% activation ratio, that is where the co-create instance takes place sometime in the distant past, and when the system is under measurement, all of the method calls are just method calls and there are no more co-create instances, you can get 800 transactions per second with a single machine. Now, when you load balance with a 100% activation ratio and only method calls, it scales just as well as in this situation. Now, it's possible that with an actual usage scenario, you'll end up with a situation where the machines are not evenly utilized, and one machine may get a little bit more work than the other because the activations aren't being rebalanced. But it would take a very uneven work distribution to account for the cost of calling co-create instance for every method call. So again, it's very important to still hold on to for the clients to still hold on to object references, despite the fact that co-create instance is the balanced unit of work. As I said, higher activation ratio will result in greater performance. And as the activation ratio approaches 100%, my test would have had to have changed and become much more difficult to run, because the database server itself would have become the bottleneck. With 2 machines, I would have easily obtained 1,600 transactions per second, but I don't think the database I was using would have been able to support that, and I would have had to scale to multiple databases as well. Eventually, the load balancing server could become a bottleneck. There is, as in all situations, a limit to the number of activations a machine can route per second. No, this wasn't it. Can I step back? Somehow I went ahead further than I wanted to. Okay. There is an effective limit to the number of activations that a load balancing server can route per second. And as I showed in that slide, this limit is affected by whether or not the load balancing server is also an application server. And this limit, the number of machines, usable machines in a cluster, is limited by a number of factors. The processing power of the cluster members, obviously. If you have very weak, very small machines, the router is, you're going to have a larger cluster in order to support the same transactions per second, as well as the relative weight of the component. And what I mean by weight of the component is how much processing power it takes to do a single transaction. For a component that takes a lot of processing power to do its work, the load balancing server will have to route fewer requests per second in order to saturate a single machine, which means that you'll scale better with the component that takes a lot of work, which is again why I used a very fast component to demonstrate the worst case scenario. And as I mentioned before, whether or not the load balancing server is also an application server affects the usable number of machines that you can put in a cluster. And you really do have to test your application under realistic conditions in order to figure out exactly how well this will work in your situation. To duplicate this test, you should use the Windows DNA Performance Kit, and you can obtain the Windows DNA Performance Kit at microsoft.com/com/resources windnaperf.asp. And with this test, you can simulate both web and MTS Com Plus performance tests. It also includes a number of performance numbers that we measured in our lab to show you the cost of using various data access methods or language implementations. And we've recently posted a new version of this toolkit, so you may want to take a look at it if you've seen it in the past. If you do this, I would suggest running the test with different components. We've included a number of them in the kit, with different activation ratios to see how that affects the scalability of these components and of component load balancing in general. One thing you want to keep in mind is that you should watch the CPU utilization on the driver machines. That is, if you have a very high or a very low activation ratio, and you're creating components for every method call, you should look at the CPU utilization on the machines that are driving these components, because the cost of co-create instance also occurs on the drivers. For example, when I had 8 4-processor machines in the component load balancing cluster, I had to use 9 2-processor machines in order to drive them, because co-create instance is also expensive on the client. And you don't want the clients to become the bottleneck in this situation, because the clients, especially in a test like this, are simulating potentially hundreds of users, and you have to make sure that, and they wouldn't in real life become the bottleneck, so you have to make sure that in your test scenarios they don't become the bottleneck. And also make sure you don't saturate the database. If you're pointing all of your application servers to the same database, especially with a high activation ratio, it's very possible that you could saturate the database with too many transactions per second, in which case the database would become the bottleneck and not your application. In the summary, component load balancing does scale, even in the worst case scenario. And the programming model, again, is unaffected by this architecture. Even though the balanced unit of work is a component activation, that doesn't mean that you should suddenly start releasing interfaces between method calls. And if you really want to see exactly how your application will scale, use the Windows DNA Performance Kit to evaluate performance and to repeat these tests for yourself. Thank you very much.